Yes. Okay, so we're recording now. As I just mentioned, I've gotten a couple questions about homework. So the system will be that I will assign problems daily, and I'll put those problems that I assign on Sakai under the tab Assignments. I hope that if you've checked out Sakai, you can see the Assignments tab and you can see what problems I assigned to you on Monday. I will assign more problems today, and then I'll assign more problems on Friday. So on Sakai, you will see all of the problems that you were assigned. However, the way that you submit your homework is by making a PDF out of the work that you've done, either by typing it up in LaTeX or by just taking pictures or making a PDF out of it, or an image file. I think Gradescope can accept PNGs and stuff like that. So you make a some file out of your work, and then you upload it to Gradescope at the correct time under assignment 1. I haven't created assignment 1 on Gradescope yet, but I will probably Thursday or something. Any questions about that system of homework? No? So that's clear? Okay. The second thing that I want to mention is I sent you all the link to the video of the first lecture on YouTube. Did everyone get that? And let me know if there are any issues. I'll be uploading the rest of the lectures to that same channel. So you should have access to all of the lectures so that you can rewatch them whenever you'd like. These cute little fruit flies. Okay, someone got an email. Excellent, thank you, Oscar. Any other questions before I start the lecture today? No questions. Is that correct? Okay, I'm gonna start. Okay, so what did we do last time? Last time we discussed what propositions are. Logical propositions. So can someone remind me what a proposition is? Oh, question, Mahita. So the homework questions are from the textbook. That's correct. The homework questions are from the 8th edition of Discrete Mathematics and Its Applications by Kenneth H. Rosen. You do need to make sure that however you're getting the questions, they're coming from the 8th edition. If you take them from the 7th edition, then the numbering is off. Yeah, exactly. If there's a free PDF of the book online, then that is sufficient to get the questions that you're interested in. Yeah, sure. Okay, so can someone remind me, what are they from the end of the chapter, then? End of the section, I believe. Yeah. So can someone remind me what a proposition is in the framework of logic?
It's a statement that can be proven either true or false, but not both.
Yep, statement. And I'll include that it's asserting a fact. Which is either true or false. Not both. Right, so the basic propositions, the atomic propositions are essentially just some statement asserting a fact. It's either true or false. And what essentially we're doing in logic, or what we're currently doing in logic, is we are developing a system of building new, more complicated propositions from a collection of more simple propositions. And we're essentially demanding that these more complicated propositions behave in certain ways. That is, they have specified truth values depending on the truth values of the propositions they're built out of. Probably that was a mouthful, but essentially, the two that we covered last time are, let's say that we have some proposition P, then we defined a proposition, a new proposition, not P. And the kind of abstract way to think about these new propositions is that if you start with some proposition P with some specified collection of truth values, then not P has some new collection of specified truth values that are somehow related to those of P. And in the case of not P, they're exactly opposite. So if I make a truth table comparing P and not P, P and not P, when P is true, not P is false, and when P is false, not P is true. So I want to emphasize that there are kind of two ways to think about what we're doing. One is a very abstract thing. One is thinking of this as just some super abstract way of dealing with these symbols that are either going to be assigned true or false, right? And then propositions are just new collections of symbols that have to get assigned values true or false based on some rules essentially that we're making up. So that's one way, one very abstract way to think about these propositions. But we can also, like the way that these things are designed are also well suited to kind of language and discussing things that appear in the real world. So if we make a proposition that says something like, it is Wednesday, then not P, the statement, it is not the case that it is Wednesday, or it is not Wednesday, it makes sense. So they do match language pretty well. Okay, that's kind of a digression. We also, for propositions P and Q, we define the proposition P and Q. Can someone tell me in words what the rules are which govern the proposition P and Q? And by that I mean, what are its truth values compared with the truth values of P and Q?
The compound to be true, P and Q have to be true. Or if
That,
neither are true, then it's always false.
that's right. So this is true only when P is true and Q is true and false otherwise. So in a certain sense, we can just think of this as a new proposition that we define with a specified set of truth values. That's one kind of abstract way to think about this. On the other hand, this reflects nicely aspects of language. So for instance, if I build some proposition like P is equal to it is Wednesday, and Q is the proposition I've been to the moon, or Mark has been to the moon, well then P and Q, which is the proposition it is Wednesday, and Mark has been to the moon, well, this is a false proposition because the proposition Q is false. So it makes sense. What I'm trying to argue is that the heart of the definition of P and Q was the truth table that I wrote for P and Q. And the fact that it matches well with our language is intentional, but not the way that we should define it. Okay, so this is our summary of what we did last time. Any questions?
Can you do one where they're not mutually exclusive?
I'm not exactly sure what you mean. So
Like for like P and Q, like is there like a combined way to do it where they relate to each other?
So the point is that the statements P and Q don't need to have anything to do with each other. Of course, it's possible for me to make propositions that do relate to each other, but that's not necessary for the construction of the proposition P and Q.
Okay, gotcha. Thank you.
Right. So here I'm kind of thinking of it as this kind of abstract logical game where If I have two propositions, I can make a new proposition from P and Q. It may not make sense. I mean, it may make sense. For instance, we could make propositions like P is equal to I study for 381, and Q is I get good grades in 381. And then the conjunction of these two statements is something that makes sense when you say it out loud, but that's not necessary for our logical constructions.
Okay, yeah, that makes sense.
Okay. Great. So what we're going to be doing today, and what will take up probably all of today and maybe even Friday, is just constructing some more compound propositions. So the next compound proposition, probably if you read ahead or looked ahead, or even if you have just poked around, you know what's coming next. Let P and Q be propositions. The disjunction of P and Q, capitals, which is written P, and here we do the downward check, and is said P or Q, is the following proposition. Is the proposition P or Q, and I'll write in parentheses, or both. So in a certain sense, this is a reasonable definition because it tells you if you have two propositions, what the new proposition is. For instance, if P is it is Wednesday and Q is Mark has been to the moon, then the disjunction of those propositions is it is Wednesday or Mark has been to the moon. Just a question. That statement, when I say it, it is Wednesday or Mark has been to the moon, is that true or false? It's true because it is Wednesday. So what I'm trying to get at is that the statement, the way that we say P or Q in language, kind of leads you to the correct truth table. But here is perhaps a more rigid or rigorous way of defining the truth values of P or Q, and is as follows. Here's the truth table. P and Q, I need to give all the possible combinations of P and Q being true or false. So true, true, false, false, true, false, true, false. P or Q is going to be true when at least one of P or Q is true. So it'll be true here, true here, true here, and false here. So I should write as a note, this disjunction is false when both P and Q are false, and it's true otherwise. Okay? And the exercises that we can do right now show why this definition of the proposition P or Q and its truth values depending on P or Q, P and Q, makes sense in our language. So why doesn't someone give me a proposition?
Great.
As homework, I am giving you all the mission to go home and prepare some propositions so that when I ask this tomorrow or Friday, y'all give me some good propositions. Ducks have feathers, great. And Q is going to be the proposition, I don't know, bananas are green. Or, yeah, sure, why not? Bananas, young bananas are green. So then what is the disjunction of P and Q?
Ducks have feathers or young bananas are green.
Exactly. Ducks have feathers or young bananas are green. Exactly, this is the construction. There's an important thing to note is that in mathematics and in logic, we will almost always use the inclusive or, which means P or Q or both is the kind of in parentheticals. So for instance, here, P is true, ducks indeed have feathers, and Q is true, young bananas indeed are green. At least that's my impression. If we say that these two are true, then P or Q, this is still a true statement. Okay? So I think that after you've seen and, or is a pretty reasonable new compound proposition that we can build. Are there any questions about it? So should we state is and or when writing it in English? I would, so what I said is that or will always, like henceforth, I will always interpret or as inclusive or. So if you say P or Q, I will always interpret it as possibly both. And that's the way that you should use or as well. Although I will come to something called exclusive or in a little bit, just as an example. Okay. So I would now like for y'all to do the following exercise. So let's let P and Q be these statements as above. So I would like for you to construct the following combinations. Would you please write out in English the following propositions? P and Q or Q. So this is a kind of more compound proposition. It's only built out of two propositions, but it's got three terms. I'm doing a conjunction and then I'm doing a disjunction. This is just, after all, a proposition, so I can combine it with other propositions. And then also write out in English P or Q and not P. So I would like for you to write out in English these two propositions with the information that P is ducks have feathers and Q is young bananas are green. Shreya, I would say that or is fine here. And Yutong, that's excellent for the first sentence. Ducks have feathers and young bananas are green, or young bananas are green. That's this proposition. Very good. So one is ducks have feathers. And young bananas are green. or young bananas are green. Good. And then can someone give me the second proposition written out in English? Morgan says, ducks have feathers or young bananas are green, and it is not the case that ducks have feathers. Yeah, very good. So 2 is ducks have feathers or young bananas are green. And it is not the case that ducks have feathers. Okay. And now what I would like for you to do is make the following truth table. So very good, everyone, on the making these kind of multiply compound propositions. I would like for you to write out the truth table. So here, I'll give you the start. P, Q, so we'll start off with true, true, false, false, true, false, true, false. And then what I would like for you to do is build a truth table so that you can see what the truth values of P or Q and not P are. I'll put not P in parentheses. And my hint to you is that in order to make this truth table, the easiest way is to make columns of your truth table which correspond to the sub propositions. So you should make a column associated to P or Q. You should make a column associated to not P. And then you can easily read off the truth value of P and Q or not P by using the conjunction, on these two columns. Does this make sense, what I'm asking you to do?
Yes.
Great. Ah, very responsive. I'm happy to see it. So I'll make it a slow race. So the race is that y'all need to beat me to this line of the truth table, and I'll be going slowly through this one. So P or Q, I know that P or Q is true if at least one of the components is true, right? That's what I just wrote on the other page. So P or Q is true when both of these are true. It's true when only one of them is true. It's true if this is true, and then it's false in this case. Y'all agree with this column? Okay, and then not P. What is not P? Can someone tell me this column? Exactly. It's false whenever P is true, and it's true whenever P is false. So it's just kind of the inverse of this column. And now what I'm doing is I'm doing the conjunction of these two propositions. And the conjunction requires both of them to be true, right? So if I do the conjunction of two propositions where one is true and the other is false, I get false. If I do the conjunction of true and false, when one is true, the other is false, I get false. If I do the conjunction of true and true, here it's true, and then false and true, here I get false. Morgan, I would say take a look at the fact that we have a true in this row for P or Q and a true in this row for not P. So since there are two trues in one, then there is exactly one true. Everywhere else is false. Right. So this proposition, which we write as here, if we go back up here, this was the proposition, ducks have feathers or young bananas are green, and it is not the case that ducks have feathers. This proposition is false because P and Q are both true. And when P and Q are both true, this proposition is false. Why is the last one false? Why is this one false? This term is false because conjunction, which is and, is only true when both of the constituent pieces are true. So if you're happy that this entry should be false and this entry should be true, then that'll imply that this is false. Right. Okay, so here, and this is kind of the game that we'll be playing for a little while, is we'll be kind of going back and forth between the kind of hard logic of how these compound propositions are defined. And so this is just essentially playing like a computer. You're all being computers and just combining true and false in the correct ways. But you can also try to go back and see how well these propositions reflect like truth in our language. So for instance, if P is the proposition, ducks have feathers, and Q is the proposition, what's a good proposition? A false one. I want a false proposition. Elephants are pink. So, oh shoot, I want it to be the other way around. I want Q to be this one and I want P to be this one. So then P or Q and not P is the statement, elephants are pink. Or ducks have feathers. And it is not the case that elephants are pink. Can you see this? No, you can't. Elephants are pink. So what I want you to kind of notice here is the way that this collection of logical connectives or these compound statements reflect well in our language, or they're well adapted to our language. So this proposition, which we built out of two true propositions, right? Here, ducks have feathers and young bananas are green are both true. And the statement, ducks have feathers or young bananas are green, and it is not the case that ducks have feathers, this is a false proposition because ducks do have feathers. So this proposition, which we built in this construction, is false. On the other hand, if we make this construction with these two propositions, namely elephants are pink and ducks have feathers, we arrive at the proposition elephants are pink or ducks have feathers, and it is not the case that elephants are pink. And this statement is true, right? It is not the case that elephants are pink, and either elephants are pink or ducks have feathers, possibly both. What I said is true. And that makes sense in this framework because when P is false and Q is true, which is the case here, then this proposition is true. I hope I'm not being confusing by kind of saying this. Does anyone have any questions about this? Lasagna is not food. Yes, that is a good proposition. I will use that for the next one. Any? Okay, I'm going to give like another couple seconds to see if anyone has questions here. Okay, well, no one wants to say anything, which is okay. How are we doing on time? Okay, we have a little time. I want to give you another exercise. Actually, I don't know if this is, you don't necessarily need to say it is not the case that when using a negation. You can do a more intuitive construction. For instance, elephants are not pink is also a valid negation of this statement, elephants are pink. It's just, it's something that will always work. You can always negate a proposition P by saying it is not the case that, and then proposition P. Okay, maybe this is something that I should assign y'all for homework. Actually, yes, I think I will. Homework, because I don't want to go through it all right now. So we use this symbol for inclusive OR. But there's also such a thing as an exclusive OR. And what should an exclusive OR's truth table look like? So in other words, exclusive OR should mean either P or Q, but not both. So P exclusive OR Q, what truth value should this column have? False, true, true, false, exactly. False, true, true, false. So essentially the exclusive OR should be false when both propositions are true, and it should be false when both propositions are false, but it should be true if exactly one of the two propositions is true. So the homework that I will give you is write P exclusive OR Q in terms of ands, ors, and negation. And the hint that I'll give you is to use the guidance from our language, which is P or Q and not both. Or P or Q and not P and Q. Does it make sense what I'm asking you to do? Okay. I think that with this hint, it shouldn't be so bad. But essentially what I'm asking you to do is find some expression that looks like P's, Q's, and a bunch of ands, ors, and nots whose truth table is exactly false, true, true, false in this setting. Well, you're not just making the table, you need to make a proposition out of P and Q and ands, ors, and nots, which evaluates to false, true, true, false. Does that make sense? Right. It's in the same way that like P or Q and not P was the proposition which evaluated to false, false, true, false. So I could ask you, find the compound proposition involving P's, Q's, ands, ors, and nots that gives you false, false, true, false, and you'd have to work to find out that, this compound proposition does the trick. That's what I'm asking you to do over here. Okay. What do I want to do next? Yes, now I want to do conditional statements. First of all, are there any questions? So we are finding a compound proposition that equals P exclusive or Q. Yes, that's exactly correct. And of course, Luke, that is also correct. You can put a not on a compound proposition. That's right. So for instance, not P and Q is something that makes sense, and you can check what the truth values of not P and Q is. Or for instance, not P or Q. You can work out what the truth values of these propositions are just by using truth tables once again. Does it make sense how you would find the truth values of these? Great. We'll do many examples of these, so don't worry if this is a little confusing. You'll do plenty of examples. What I now want to move on to are conditional statements. Okay, definition. Let P and Q be propositions. The conditional statement P right arrow Q, which is read if P then Q, or P implies Q. And there are actually a whole ton of other ways. Oh yes, absolutely. Also, I can't trust myself to always read the group chat, so just letting you know that you can always use your voices. Okay, conditional statements. If P then Q or P implies Q, is the proposition. So here I've told you how to build the proposition. If you have two propositions, then the conditional statement is if P then Q or P implies Q. And then this is the symbol that we'll use. And then I need to tell you its truth values. So P implies Q is false when P is equal to true and Q is equal to false, and it's true otherwise. So what I can next do is build for you the truth table. P, Q, true, true, false, false, true, false, true, false. So what I said is that P implies Q is false in exactly this case, and it's true otherwise. Okay. This one is what usually ends up causing people some trouble. If P and Q are unrelated, then these are the truth values. So this is the answer, Catherine, to your question is that this is simply a logical construction, and P and Q don't need to have any relationship at all. I'm building a new proposition with the following defined truth values. So that's this collection. So this is kind of the abstract way of thinking about it. Is there a question?
Shouldn't be true, false, true, true.
Say that again.
False, true, true. For the if P then Q.
I think she's right, actually. It would be.
Oh, did I make a mistake here? Yeah, I did. Sorry. I did. false, and then true. Yeah, I just mixed it up on the page, sorry. Exactly. So this proposition is only false when P is true and Q is false, like I wrote here, and then it's true otherwise. Thank you so much. Okay, and to Catherine's question, the propositions P and Q don't need to be related at all. It just has the following truth values that are assigned here. So let me now do some examples. Yes, this is the question that everyone has, is why does it work for P is equal to false and Q is equal to true? So let me do the following example. And this is an example in the book, which is a very viable example. Let me make the following statement. So P is equal to the statement, if P is the statement, you get 100% on the final. And then Q is the statement, you get an A in my class, in this class. So can someone tell me in words what the proposition P implies Q is?
Yes, 1%. 100%. Fine.
Yutong, I'm having difficulty hearing you, but what I think you said is if you get 100% on the final, then you will get an A in this class. Okay. My proposal is the way that you should think about this is you should think about when, if I tell you this, when did I lie? Okay, so let me write down the truth table again. PQ, P implies Q. So true, true, false, false, true, false, true, false. And then if I do this right, this is true, false, true, true. Okay, so let's do this. Let's kind of play out the situation in each of these cases. If you get 100% on the final and you get an A in this class, did I lie to you if I said, if you get 100% on the final, then you will get an A in this class? No, I told you the truth. I said, if you get 100, you get an A. You got 100, you got an A. Okay. Next, let's kind of skip this one and go to this one. Did I lie to you if, well, no, let's not skip this one. This is saying you got 100% on the final and you didn't get an A in this class. Did I lie to you when I made this statement? Yeah, I lied. This statement was a lie if you got 100 and you didn't get an A, because this told you if you get 100, you will get an A. Okay, so in that setting, this line makes sense. The next line is, if you get 100 on the final, you get an A. Let's say that you didn't get 100 on the final. Is there still a way that you could get an A? Yeah, say you got 99% on every single assignment in the whole class. Well, it's false that you got 100 on the final. It's true that you got an A. Did I lie to you when I said, if you get 100 on the final, then you'll get an A in this class? No, I didn't tell you a lie. What I told you was true. It's just that the hypothesis, which is the first part of the statement, wasn't satisfied. So what I'm telling you now, or what I'm going through now, is why does the language that we built up around this proposition, and the language is if P then Q, why does that make sense? Why does that produce kind of consistent results in language when I write out what this proposition is in terms of truth values? And then the last one, of course, also makes sense. If I say, if you get 100% on the final, then you'll get an A in this class. If you don't get 100% on the final and you didn't get an A in this class, I still didn't lie to you. So the only time that I lied to you is if you got 100 but you didn't get an A. So Stefano, is it necessarily true that 100% on the final guarantees an A? So the if I tell you that this proposition is true, like if this proposition is true, which of the following scenarios could occur? And it's correct that I don't know what the the syllabus said. So once again, sorry, not matching this to real world stuff. There's another very compelling argument that I want to do that's a little looking forward in this class, but I still think it's good. Let's consider the following statement. If 4 divides x, then 2 divides x. Okay, so we haven't really gotten to this, but I still think this is a good example to examine. So let's say where x is an integer. So this right now is not a proposition, but every time that I can plug in an integer, then it becomes a proposition. So for instance, here's a proposition. If 4 divides 8, then 2 divides 8. Is this proposition true or false? This is true. Okay. The point is, we want this proposition to be true. If 4 divides x, then 2 divides x. And what it means for something to be true is that it needs to be true always. So if I want this proposition to be true always, which is the meaning of true, then what truth value do I have to assign to the statement if 4 divides 3, then 2 divides 3? What truth value do I need to assign to this? This needs to be a true statement. And so this is kind of helps with the understanding of why, let's say this is P and this is Q. Well, P is false, Q is false, P implies Q is true. Does this at least kind of help with the ways of thinking about why this thing should be true when P is false? Yeah, so this line is the one that kind of gets people. Or actually, I don't know which one gets people. Maybe both of these lines get people. And the two ways to go about this are, one, to just take this as a definition, which is the kind of abstract thinking that works in this class. But the other way to think about it is to remember these examples about thinking of it as kind of like a contract, where you have the hypothesis P and then the conclusion Q, and you say, when was this a lie? And this was only a lie, or this was only false when the hypothesis is true, but the conclusion is false. So with P implies Q, we are assuming its truth value as true until proven otherwise. That's a way of thinking about it, yes. So P implies Q is true unless it is proven false by P being true and Q being false, and then it's false. This bottom line will be false if you change the statement to if and only if. So we haven't gotten to if and only if, but if and only if will be true when both statements are false. Okay, we are about out of time. Does anyone have any further questions for me? I would definitely say that these are two helpful examples to remember why the truth table is this. But at the end of the day, the important thing for you, well, there are two important things for you to remember. The first is this is the truth table for P implies Q. And then these are good ways for you to rationalize or help make sense of why these entries of the truth table make sense and why they are compatible logically with the way that we think about language. Great. Could you write a sentence for P being false and Q being true? I mean, sure. So let's say macaroni is not a food, or lasagna it was. Macaroni is not a food. This is P, and P is false. False. And then what's a true statement? Oh, yeah, I'm sorry. And then Q is the statement books have pages. And this is true. And so the proposition P implies Q is macaroni is not a food. Or sorry, if macaroni is not a food, then books have pages. And this is true because macaroni is a food. So all sorts of kind of counterintuitive propositions become true whenever you have an implication and the hypothesis is false. So if unicorns exist, then I am a billionaire. This is true because P is false. Q could be true or false. In this case, it's false. But this proposition is true by our rules of the truth table. And also, this makes sense to be true, as kind of wacky as that sounds. Is this okay? All right. Well, I look forward to seeing y'all on Friday. Yep. Have a nice day.
Thank you.
Yeah.